Okay, good afternoon, everyone. It's my pleasure to introduce Dr. Malintha Fernando, who's a postdoctoral fellow at Digital Futures, coming here from Indiana, University of Indiana in the US, where he got his PhD last year. And he's been working on cooperative control under communication constraints with heterogeneous teams. And now he's going to be telling us about graphical methods for multi-robot control in mixed competitive cooperative environments.
Thank you. Okay, so good afternoon, everyone, and thank you, Pedro, for the introduction. So, yeah. My topic for today's presentation is graphical methods for multi-robot control in mixed competitive cooperative environments. I want to start by showing some really cool video. Some of the motivation for my work comes from an application called advanced air mobility. Briefly, that refers to using this type of drones to transport cargo or passengers over short distances. And this drone was developed by a company called Joby Aviation in California. They are working on developing a vertiport network in the Manhattan. And you might have already seen this one. This is from a company called Zipline. They have been operating in Africa for a while, delivering medical products, and now they are expanding their operations in the mainland US. So now we have these really fancy drones and autonomous taxis. I think the next immediate question that we want to ask is, these vehicles are not going to operate in isolation. They have to coordinate their actions and their trajectories with all the other vehicles in the same region to serve a fleet's objective. So, for example, we can have objectives like fulfillment ratios. So that is like how much requests that I have completed in this region, and then economic revenue, because there's no point of fulfilling all the requests without earning money. Then also passenger waiting, minimizing the passenger waiting time in the city, and things like that. But the challenges are when these fleets get increasingly large, then solving these optimization problems as a coordination control problem is not always straightforward. For example, we have the original problem of scalability in the number of robots. Like when we have a large number of robots in this fleet, it's not always feasible to coordinate them from a central location. And the other thing is, we want to also expand the service area. For example, sometimes if the city of Stockholm decides, okay, we need to expand to a certain other region, then we should be able to deploy the same fleet without doing a lot of tweaking into the island policies or coordination policies. One of the motivations for this type of scalability-related issues is coming from this documentation, that is the UAM CONOPS. That is a documentation from Federal Aviation Agency. They outline their vision for advanced air mobility ecosystem. How should these type of drones share the aerospace? How should you allocate the bandwidth for them? What type of autonomy that these vehicles should have? All of these things they have outlined in their documentation. And the other problem that I want to address in this talk is the problem of heterogeneity. The heterogeneity, I think, can arise from two factors. First one is the physical traits, easy to imagine. You can have heterogeneity in the capacity, range, etc. And the heterogeneity in intentions. That is, do all the robots that I share my space with belong to the same fleet? So all of us serving for the same reward function or same utility? Or do we belong to different fleets that we compete with each other? And so these are the heterogeneity in intentions. Here we have some robotic literature that are related to the content that I want to talk today. First, we have the classical control based coordination of multi-robot systems. Basically, we can come up with an control rule for the robots or the entire fleet, so it could be distributed or centralized. And we can also list the task assignment and trajectory optimization based methods under the same topic. In this case, we can do a task assignment using scheduling or Hungarian algorithm. Then we can use trajectory optimization to calculate what the trajectories this robot should take in order to go to the task location and fulfill these tasks. And then On the other side, we can have more novel approaches like reinforcement learning. In this case, we might be learning a policy characterized by a set of neural network parameters to solve a problem. So in this case, we can have MDP like Markov decision process like formulations. They are also like coordination control like methods. Then we can have agent-based modeling. In this case, we can treat sometimes all the agents share the same reward function, or they can have different reward functions. If they're competing, then they give rise to a game. If they are not, then we can have decentralized MDPs, different types of Markov decision processes, but they serve the same reward function. And we can also have some game theoretic formulations that are beyond the reinforcement learning literature. In this case, I would like to narrow my focus to this specific type of games called the graphical games. I want to start by showing some work that I did in my PhD under the coordination control. Then I would like to move on to the other methods. And so in this case, our objective was to maintain a formation of UAVs. We have a human operator. The human operator has an objective that is to send these UAVs in by maintaining a certain formation. And human operator may define this formation by using a shape vector. And it will give a set of waypoints or a trajectory that in this case acts as a virtual leader to guide this formation in the environment. And then we use a centralized planner to offset the locations of each individual robots from the virtual leader and then calculate its own trajectories. And in the case of singularities, we use task assignment to recalculate the goal locations of the robots. For example, in this case, they want to rotate by 90 degrees, so they use a task assignment algorithm to do that. And we recalculate these trajectories using trajectory optimization and execute them in a receding horizon fashion so we can have continuous trajectories in the environment. Right, so all these coordination control methods, they are all nice and small as long as we can aggregate, we can make certain assumptions. But when we increase the number of robots, as I said before, we are going to have scalability issues. A classical problem that we had in the US was about a couple of years ago, the entire air traffic control system went down. About 20,000 flights has to be landed. So in that CONOPS, what they are actually proposing is, no, don't do centralized coordination. Always try to delegate more autonomy for the vehicles. And we also have problems of communication. If we want to expand the service area, and when these robots are spreading over large distances, then we cannot aggregate the necessary global storm state to calculate the global coordination. Then when we have a large amount of heterogeneity, incorporating this heterogeneity in a single objective function can also be difficult. That is also something that I would like to avoid. So to solidify my argument about the communication, we ran some simulated experiments. We created a UAV swarm that each UAV has a router, wireless router associated with it. Then we set them off in different directions. Then we measured the received signal strength between each of these robots. What we found was when the distance increases, the stochasticity of the received signal strength also increases. And on the right-hand side plot is the network topology. When the distance increases, the system becomes increasingly fragmented, and at a certain distance, all the robots getting completely disconnected. And at large distances, the probability of having a link is also very low. So the key takeaway from this slide is the state aggregation and the guarantees of the network topology we cannot provide at large distances. So in these settings, we want to come up with a method to do distributed cooperative coverage. The setting for problem is like this. We have a set of UAVs, and each UAV has a wireless router, and we have a set of ground robots. And these ground robots can be stationary, or they could be mobile over the environment. So our objective is to use these UAVs to establish a wireless network for the ground robots. And we should also be able to maximize the bandwidth within this communication network. So we proposed a method based on probabilistic inference over Markov random field for cooperative control. First, we take this communication, we take the interaction topology given, right, caused by the communication topology. Then, for example, if we look at this black robot, then if we consider the one-hop communication topology, then black robot can talk to 3 blue robots. Then the intuitive, what we want to do is come up with some objective function, maximize this objective function of this black robot. So MI in this case is the black robot's objective function conditioned on the state of its local neighborhood. But so we want to calculate the probability distribution over its actions, which are xi, and the marginal distribution of that is the qi. But if we do that, the problem is it is not cooperative. Now, black robot is choosing its action unilaterally, so it induces some perturbation into the local neighborhood, because if it chooses its action unilaterally, then that action might be causing a negative impact on a blue robot. So what we can do is we can change this utility function into something that depends on all the state of all the agents. And now we just not want to draw a single action. We want to draw an action profile for the entire robot, entire neighborhood. And we want to maximize this utility function. So we still have the same perturbation if one robot chooses its action and then it induces perturbation. So what we can see is this is similar to a Belief propagation on a random field. So that was the motivation. We take this original local graph we call it an interaction hypergraph or coordination graph. And we take this interaction graph and then we add more edges into that. For example, I can add more edges for the neighboring robots, blue robots, and then I can consider that as the Markov random field that I want to do probabilistic inference over. So I have a set of hidden variables that are the marginal distributions of the actions of each robot, and then observable variables are the states of the robots. So another problem that we had was, okay, what will happen? There is some state variable that actually does not depend on the agent's state, but that is dependent on something else in the environment. So we can also incorporate that as an additional variable into the system. So this orange color node can account for this type of states in system. Then we can use Gibbs distribution to factorize this Markov random field. Essentially, the big idea is the posterior distribution of this Markov random field is proportionate to a set of pairwise functions and a set of unary functions. And then we can normalize this by using a partition 1 over C. So the point is, okay, if we can come up with a set of functions that depends on the state of 2 robots and a set of functions that depends on the state of 1 robot, then we can maximize the probability distribution over this we can use these functions to evaluate the posterior probability distribution. So how did we do that in this communication problem? We looked into the wireless communication literature, and then we found that, hey, there's a function, we call it psi r, that we can use to calculate the expected received signal strength between any 2 points in the environment. So here T naught and L naught are based on your network conditions. And we use that as the pairwise factor, because if we can calculate the signal strength between any 2 robots in the UAV swarm, then if we maximize that, then we can maximize the bandwidth. Then how do we calculate the unary factor? We have the region of interest. And for any point in this region of interest, any robot thinks, okay, what is the highest received signal strength either I or anyone in my neighborhood can impart on this point, and then take that maximum value. Okay, then we multiply that with the probability of having a robot at that particular point, having a ground robot at that particular point in the environment. So here we have a visual representation. First, we take the ground robot distribution and then calculate the team abstraction of that by using this work. Basically, we can come up with ellipsoidal or rectangular team abstraction for that. Then here we have the one-hop communication network of the red robot. Red robot knows the existence of the yellow robot and the blue robot, but it does not know the existence of the gray robot. And based on this unary potential function, the red robot thinks, okay, all of the points in the blue region are best covered by the blue robot. All of the points in the red region are best covered by myself. But because it doesn't know the existence of the gray robot, it thinks, okay, all of the points in the rest of the region are best covered by the yellow robot. Then we have the two unary and pairwise factor potential functions. Then we scale them up by using two scalars alpha and alpha b to calculate the utility under action profile of a single agent. So this utility function is actually a factorization of the global utility function because now the red robot cannot actually calculate the global utility function because it does not know the state of some other robots in the fleet. So this is a factorization of the large cooperative reward function, but individual agents are trying to maximize their own utility. Still, the utility is a cooperative utility function. So now I want to do a little bit of analysis. There's a concept called graphical games in the game theoretic literature. The difference of graphical games to the normal form games is in a normal form game, one player's utility may depend on everybody else. In a graphical game, we define this game over a graph. So one robot's utility only depends on all of its neighbors. So it's a simplification from the normal form games. And there's a theorem that if you can synthesize this interaction topology of a graphical game over to a probabilistic graphical model, let's say a Markov random field, and if you can calculate a posterior distribution over this Markov random field, this posterior distribution is a correlated equilibria for the graphical game. So, but the problem is, if we have a large number of robots in the system, taking the whole interaction topology and then doing exact inference on this to calculate the posterior distribution is going to be very hard. For example, if you have a very large action space, this is going to be really difficult. So we relax this by using a mean field assumption. Essentially, what we think is the joint posterior probability distribution is in fact the product of the marginal probability distributions. So we assume that the marginals are independent, but it's not a great assumption because now when we do that, we assume the robots can actually choose the actions independent of one another. But the good thing is it gives us an iterative update rule that is very fast. So we can use the variational mean field inference to come up with this update rule. And finally, we can calculate the mean field posterior distribution that is the product of the marginals. But the problem was it is not a correlated equilibria anymore, but we can show it is at least a mixed strategy-Nash equilibria. Then we ran the experiments on this method. We implemented this on robot operating system and network simulation. So basically, in the robot operating system, we can calculate the robot's physical actions and then trajectory optimization, low-level control and everything. And we delegate the network routing and calculate the received signal strength and everything to the network simulation. So in this case, we have a UAV swarm of 3 robots on the left-hand side, and the ground robots are the small blue dots. And on the right-hand side, we have UAV robots of 8 UAVs, and the ground robot distribution is the same. And we let them set off from the center, and we can see the communication topology changes over time. And on the bottom is the average received signal strength of a ground robot. So we can see that they managed to cover this area pretty reasonably. So this is also, not that this is a very large region of interest. It has 22,000 square meters in it. So what will happen if we set these ground robots move around in the environment? The UAVs can still squeeze themselves into the region of interest, and that is also in real time, which is very fast in computation. Actually, yes, I want to show the computational time for that, but I want to I will just tell you. So we were able to compute the computation time for one iteration of optimization under 24 milliseconds for a very large region of interest. So the most of the computation actually took for the integration step over the points in the region of interest, but it was very fast. And then I want to see, okay, how will this happen if we change the objective to something from the flocking? So in the flocking, what we expect to see is something like this. These robots need to get close to its neighbors, but not too close, so they would crash, but they want to also fly in the same direction. So that is, in general, the flocking objective. Then we calculate this interaction graph based on the nearest neighbor topology. And then we added the additional edges that we want to in the Markov random field, and then we did the optimization. The factor potentials that we used are from the self-propelled particle model from the this statistical physics literature. They are similar to something called Morse potential functions, and I would like to refer to this paper in ICRA for more information. Then we did the experiments again, and we can see they get very close to each other, and there's a point. This purple color point is an external point that all the robots would like to get closer to, and we incorporate this into the optimization problem as an external node, as the orange color node that we saw before. So these are the real UAV experiments. I used Spacefly UAVs for that, and they managed to get closer to each other and then make this beautiful pentagon-like formation and then fly in the same direction near the center of the environment. Right, so this is the end of the first part of my presentation. In this part, we discussed the pair for value function decomposition when we cannot aggregate the whole global swarm state, and then we optimize the one robot's objective function, but it is still a cooperative objective function. And we use mean field variation inference to come up with an update rule, and we show that this will result in a mixed strategy for the stage graphical game. And we also deploy this in flocking and coverage problems. So now I want to step into the second part of my presentation. I want to give it a little bit of boost by adding more stochasticity into the system now and adding more heterogeneity into the system. So stochasticity in this case actually arises from two factors. Stochasticity that comes from the agent's decision making. All the agents try to make decisions, but you don't have all the observations about what they are going to do. So that gives some stochasticity. And we have stochasticity in the environmental processes as well. So the problem that I'm going to discuss here is an advanced air mobility problem. We have a set of vehicles. They can have different carrying capacities, small, medium, and large. They interact with a set of depots in the system. And these depots populate set of payloads into the system that are also small, medium, and large. For example, the largest robot can carry small and medium payloads. So the interaction graph in this case is not an homogeneous graph anymore. It is an heterogeneous interaction graph. This is the meta graph for this particular scenario. We can represent the interaction of vehicles and depots using a specific edge type that we call the visit edge, and the interaction between the payloads and the vehicles as an assigned to type of edge, and so on and so forth. The big picture is that, okay, now we want to use the observations of the robots that are instances of this metagraph, and we want to learn the policy based on a graph neural network to coordinate these robots. And we published this work in last year's RSS. We formulated this mobility problem as a game. At the beginning, we have a robot, and we mark this robot as an available robot, and it can observe the local environment, i.e. the depots nearby, and each depot indicates the availability of different types of payloads with them. Then the vehicle uses a learn policy to choose a depot that they want to go to next. The depot uses a payload assignment function to assign a payload from its queue to the vehicle. And at this point, we mark this vehicle as an unavailable vehicle. And finally, this vehicle travels to the depot, picks up the payload, and delivers it to the destination. And we give this robot a net revenue, and we mark this vehicle as an available robot again. So it is free to undertake another payload. So our objective function for this problem is to find a policy that maximizes each agent's local revenue over the long horizon. So let's consider this multi-agent game problem. Everybody makes these actions simultaneously. We have a set of 3 robots, and they have 3 policies, pi1, pi2, pi3. Each one of them receives an observation from the environment and a reward signal. Then they use their policies to choose an action. So what we would like to do is to come up with a policy that can generalize to different levels of capacities. How did we do that? We defined an observation function as 2 components, observations that come from itself, that is hi, and the rest of the observations comes from the environment. And hi has the states of its current location, next location, and the capacity. So this policy becomes a conditioning based on its capacity. So the idea is, okay, if we change the capacity and if we simulate this system, so then robots will explore the system and understand what's the actions and the rewards that they can undertake, and then it will learn to generalize to different capacities. And actually, we can do that in 2 ways. We can use one policy that generalizes to all the capacities, and we can use a policy for one capacity. In this work, we actually found that we can learn a policy that generalizes to 3 different capacities very well. So each robot receives a local observation. Then we use this metagraph signature to compute its observations, its interaction graph. For example, in this observation that this agent received, it has observed 2 vehicles, 3 depots, and 3 payloads per depot. So it has 9 cyan color nodes that represent the payloads, and then 3 depots, purple, and then 2 vehicles. So this is what we are going to put into our policy and then use to calculate an action. The good thing about representing observations in this type of heterogeneous graphs is they are very expressive. So if you have a very complicated environment, we can explain what's going on in here. And we can use them to preserve the asymmetry between the nodes and encode semantic information between these nodes. So before I go any further, I want to discuss something very briefly that is called the graph attention neural networks. In graph attention neural networks, what we have are features associated with each of these nodes. And it is a convolution type neural network. Essentially, we are learning a convolution kernel that over the edges, so we can pass these features through the convolution layers and then calculate projection. For example, I have two nodes here, ith node and the jth node. Each of them are associated with hi feature and then hj feature. And we have a weight matrix W, and then we project these into a different space. And then we take this projected feature space and then send them to an attention neural network, or IE, a linear neural network. And then we take this output of the linear neural network as alpha ij. Basically, alpha ij is the normalized value over output, or normalized output of the attention neural network over its local neighborhood. So then we calculate the updated feature vector of the ith node as a weighted average. So we would like to use this in our problem, but the problem is our method, our observations are now heterogeneous. They are not just homogeneous graphs. So we propose using a relationship-specific node-level attention. For example, in this case, we have 3 types of relationships between these red nodes, green nodes, and the blue nodes. So the attention scores are actually normalized within the nodes that share the same edge type. For example, these 2 red nodes has the same relationship to another red node. So the attention score comes to 1 within these black nodes. So the good thing about that is it helps prioritizing nodes within a given type. For example, now this red node can calculate what is the importance of hi versus hj to me. Then the other problem was the projection matrices. Projection matrices should be also, we cannot use the same projection matrix across all the relationships because they can have different size feature vectors. In this case, we use a relationship-specific weight matrix. So the W phi is specific to a certain relationship. So the good thing about this type of graph neural networks is it does not matter how big your input graph is, as long as this graph is an instance of the same meta graph that you trained your neural network on, it will generalize. So we have a payoff function for training the robots. Each robot has a payoff that is a quadratic function of the starting location and the destination, and everybody gets a small payoff depending on the size of the payload that they delivered. So if they delivered a larger payload, then they receive a higher payoff. And this function is also a concave function. The first Q1 coefficient is smaller than 0. We found this concavity helps the agents discourage. This function discourages the agents from always choosing long distance rides. So otherwise, if you have a linear function, we found that these robots to always go to one end of the city and then just stay there and then go to the other end of the city. And we will not have a uniform distribution of the robots over the city. If the robot chooses a depot that does not have a suitable payload, then we penalize this robot. Then how did we use this graph attention, heterogeneous graph attention layer to calculate the actions? We proposed a graph attention encoder-decoder architecture. First, we have these observations that are graphs and the features associated with the nodes. Then we calculate the heterogeneous interaction graph. The input for the encoder part of the neural network is this heterogeneous interaction graph. Then we process this input graph over a couple of neural network layers, and then we take the output feature vectors of the depot type nodes, vehicle type nodes, and the payload type nodes, and then we take the average node of each type, and then we concatenate all of them to create something called a summary node. So we think is a good representation of the original observation space. Then we have the decoder. In the decoder, we create another graph that's between the summary type nodes, payload type nodes, and an additional node that we introduce called the value node that is for the reinforcement learning purposes. Then we send it through another couple of graph neural networks layers, and we take the output projection of the depot type nodes. And we consider these depot type node outputs are the actually Q values associated with choosing a particular depot. Then we choose the depot that has the highest probability and has them for execution. For the training, we use a specific learning scheme. Basically, we train these policies for a non-on-demand environment. That means the payloads have only been populated once. Then we train the system on this environment. Then we did a zero-shot transfer to the on-demand environment. The main problem was because the demand patterns can change with time and city. And also, you may start with an environment where you have abandoned payloads to deliver, but then as you deliver them, your system becomes increasingly competitive. So you start with a generous sum game, then now you are getting closer to a zero-sum game. So your policies should be able to tackle both of these problems. So this is the training plot. I compared that to general graph attention and graph convolution, and we found that encoder-decoder can perform the best. The training wasn't too terrible either. So on a reasonable desktop, we were able to train this within 8 hours. These are some transferability results. So in the on-demand environment, we have the green box on the left-hand side is the policy that we propose. Basically, we have the encoder-decoder policy, and then we also we took the same policy, and then we did another experiment by masking the depots that we know do not have any suitable payloads for the vehicle. So it's something that we can do because we can actually observe the observations. And the benchmark that we use is a linear assignment method. So we can think of it as some kind of a socially optimum assignment. So from the fleet completion, payload completion front, we found that our methods to perform within about 6% of the linear assignment method. And then we changed this environment to a more competitive environment by reducing the payload population rate, and we found that it to be still within a very reasonable margin of the socially optimum assignment. Then Another thing that I discussed at the beginning was that these policies should be able to scale. We should be able to arbitrarily add or remove the robots from the system. So we trained the system for 6 robots. Then we increased the number of robots in the system. And I maintained the same fleet composite ratio between the small, medium, and large robots. And we found that it do respond accordingly. When we have more number of robots in the system, it was able to get very close to the linear assignment-based payload completion. And finally, we want to change the fleet composition and see how this thing will perform. So we take this base environment on the left. So you have small vehicles, medium vehicles, large vehicles, and then the fulfillment ratio and the total revenue. And then we added more depots in the system and without change. And we also added more large robots into the system. Actually, we added more robots into the system as well, and then it responded by increasing the fulfillment ratio. Then we replaced the small robots with larger ones. Essentially, we added more large robots in the system, and now the total completion ratio increased because now large robots can deliver more packages than the small robots. This is also a very interesting graph. So here what we did, we increased the observation radius. Previously, they were able to observe 33% of the depots in the environment. Now we increased that up to 100% without retraining the policy. So it's the same policy. And it was able to respond very well. In fact, it got close to the social optimum assignment with the global knowledge. So that was all the content that I want to present today. And I have some future work based on this presentation and also the multi-agent topics that are pertinent to this. So one of the things that I would like to do is couple this with a centralized scheduling mechanism to minimize the price of the anarchy. That means the price of the anarchy is the cost that you have to pay because these agents are selfish. I think one way that we can minimize this is by using the results of the linear assignment-based method or some scheduling-based method to reinforce the learning process. So it is more like an imitation learning-based mechanism. And the other one I would like to do is extend this work on the to generate on-the-fly coalition forming for heterogeneous swarms for multilaterally evolving environments. It's a lot of words. Basically, let's consider that we have the depots, and depots can decide which robot should I pick to assign a certain payload. So that is now a multilaterally evolving environment. The depots can also make decisions. Another application for that type of works is, let's consider this wildfire scenario. We have fast spreading wildfire and a small wildfire that is spreading slowly. So when we want to assign our robots or the resources, typically there is a human who decides, okay, I will assign 50% of my fleet to the this wildfire and the 50% to this wildfire. But this is subject to the human bias. So can the robots make this decision by themselves? As the wildfire spreading ratio changes, if they can make a different coalition and move the other side. So these are some open questions that still falls in the multi-agent RL literature. So that's all. Thank you.